This talk is about how we are scaling Uber's data, the big data platform, right? So we have a pretty tight agenda, so trying to get you a lot of systems that we've either contributed or are opening up to the community. So my name is Abhi. I'll be introducing why data is important. Maybe all these previous sessions have already given you some feel for that, but I'll also talk about the challenges that we're facing. Then Reza is going to talk about how we're taking, providing minutes level of data freshness at the petabyte scale. Danny will come and talk about our ingestion and egress platform that we've built for this big data system. And then Ekant is going to see how we are scaling HDFS at Uber, right? So quick intro on myself. I am the Eng director on the big data team, and I've been here about 2.5 years, and it's been awesome fun. Right, so Uber's mission is to provide, to ignite opportunities by setting the world in motion, right? So every experience at Uber, we want it to be magical. Like you push a button, a car shows up, you push a button, food shows up, and behind the scenes, data is powering a lot of these experiences, right? So one example that we take is on your left, right? You open the app, even before you've typed in a destination, based on your location and history, we know which destinations you might be interested in. So that's being powered from data. You select a destination, we show you prices like fares for various offerings like UberX, Uber Pool. Those fares are also being provided from data. Now, this is like historical data being used. So from point A to point B, we know all the past trips that happened. So we know what the price should be. But then we also use the near real-time data. We use weather data. We use like local events, the current traffic conditions, all that to price in what should the fare should be. Then in the middle, we have driver partners who need directions. We obviously have driving directions, but now we are also doing walk-in directions for the delivery partners, for restaurants. And on the right of the screen is similar experience on Eats, right? We are constantly looking at the ETA times, using data. You'll be looking at the recommendations that we should make for your choices. And then even within each restaurant, we are trying to personalize and figure out which menu items you prefer. So data is powering all of these experiences, and the key is to keep it magical, right? But behind the scenes, what are the challenges? Now, one big challenge based on the title of the talk is scale, right? So from a scale point of view, things are growing, and they're growing more and more rapidly with time. So as you can see, the fun fact, the first billion trips took almost 5 years. But the most recent billion trips took under 3 months. And we recently hit the 10 billion trip mark in June. And so this trend is accelerating. But for the data team, we need to accumulate data from the first trip that happened in Uber. Right? So we have all that data. We have all the associated data across continents, 60 plus countries, 600 plus cities. So volume is a big problem and a challenge. The second challenge is offerings, right? So again, this is an acceleration of offerings. We initially had Uber Black, then Uber X, Uber Pool, Express Pool, Uber Eats, Freight, Bike, Health, and it's just going to get faster, right? Based on the things that are in the pipeline. So what this does is that for each new product offering, we not only have like riders and drivers or a similar concept and the trips, we also have maybe restaurants in the case of Eats. In the case of Freights, we have shippers. And so there's a lot of new flavors of data coming in. There's third-party data being ingested. So the variety of data is increasing. And the third is the consumption of the data is becoming more and more diverse at the company, right? So we have 6,000 plus data scientists, engineers, and city operations folks who are constantly using data in some form or the other to run their business, right? So for example, the city operations folks, they're spread across the planet, and they are constantly looking at interactive dashboards or making ad hoc SQL queries, because they want to stay on top of the pulse of their region, right? They want to react to events happening. There could be congestions, there could be a baseball game that's ending late, so they want to send drivers to that rather than at the time that was predicted, and so on. So they are staying on top of their business. Data scientists, on the other hand, are taking that historic data and sort of continuously looking for patterns, weekly patterns, daily patterns, yearly patterns, seasonal patterns. What happens when it rains? What happens, things like when a Caltrain breaks down. So they're looking at these kind of patterns and figuring out what's the best way to train models. And engineers are also using data to either have rule-based systems for spam, and there's a lot of fraud. Where there's money, there can be fraud, so they're constantly trying to pick up on these signals and building systems to catch these problems. So volume, variety, growth, and then in terms of numbers, what this means is that, right, we have multiple data centers across. Traditionally we have like East Coast, West Coast in United States, and now we have a few other presence. So 20,000 plus machines on all these data centers and regions, 100 plus petabytes of data, ton of compute capacity, a million queries on Presto and Hive in a week, hundreds of thousands of Spark jobs, 2 trillion messages on Kafka ingested per day. So, like this sheer scale of this is sort of some handful of companies have seen this. So that's a big challenge, right? So based on all these challenges, right, let's see how we have scaled, how we have sort of overcome. And based on this session, you can see that the open source has been a key in terms of dealing with these challenges, right? So we, as Tuan mentioned in the morning, we have a great community. We have been, participants both from taking from the community, and now slowly we are giving back, right? So we've built the foundations of our big data system by embracing the standard technologies, right? So that includes Spark, Hive, Presto, HDFS, Yarn, Parquet, Kafka, and so on. So that's like the basics, right? But we haven't just stopped here just because initially maybe it did work, but as you can see, with some unique scale challenges and some unique features, these systems had some shortcomings. So we sort of built up teams, and we started looking at these problems, fixing them. It could be bug fixes, small features, and now we are like on a bigger features, and in some cases we are leading the thoughts, right? So some of the unique features that we sort of deal with, as you can see from previous talks, is that we have a lot of geospatial data. So geospatial joins on Presto, for example, were not that optimum. Facebook and other companies may not have needed that yet. So we worked on that and we contributed that back. And similarly, HDFS, we are reaching scale that requires some sort of, federation that is new in this open source community. So Ekant is going to talk about that later today. And not only sort of embracing and contributing back, but when we started, there were some systems which are not even in open source that we had to build, right? One clear example is the near real-time data. So as I said, like as Uber, so things are happening in the real world. We need to mimic that in our internal world, because the faster we can mimic things happening in the real world, the better insights we have and the better decisions we can make on that, right? The world of ETLing and waiting for 24 hours before data reaches data analysts or data scientists just means that we are flying blind for that amount of time. So we had to build, incremental ingestion systems. We had to build a platform for ingress and dispersal of data for a variety of sources and sinks, and those are Marmara and Hoodie. And we are going to talk on today's talk on these two also. And we have also built some other systems that will come and that we have open sourced on our own, right? So we'll talk about that very briefly. So that's the open source philosophy. right? And so that kind of derives the mission for our team, right? So we want to be the team that ingests all of Uber's data. We store all of Uber's data in one data lake so that everyone can join all this data and get meaningful insights. And we want to be providing processing engines that sort of cater to each type of the use case. So we just not a Hive shop or a Spark as one engine. We want to be having different use cases satisfied with a diversity of the processing engines. And all this so that we can surface or help surface insights that others can use to make every decision at Uber. That's the goal, right? And so in terms of pictures, like the high-level obligatory diagram, what this looks like is that on the top left, you can see that we have all the microservices. These microservices are reacting to either user events coming from the app, or they're just like recording what the GPS is or the other events that is being processed. And those events are getting streamed into Kafka. Right. Similarly, the databases like MySQL, we have something called schemaless, which we have blogged about. It's a sharded MySQL key value store internally built. And then there's Cassandra. So all these databases are also storing state, and this state is also getting streamed in form of change logs into Kafka, right? So we're not snapshotting the databases and uploading them into the data lake. We're sort of streaming the change logs as they come into Kafka. This is key to be able to at least collect everything that's happening in the system on the real online sort of user-facing aspects of the system into Kafka. And then we use the ingestion platform called Marmoray to incrementally ingest it into HDFS. And there we use something called Hoodie. We'll be talking about that today. And with Parquet to provide that, that fresh data view. So that's like the focus of the talk today, but just to complete the picture, right? So above this, we have Yarn and all types of ecosystems for various use cases. And just a quick plug, the next session after this is going to be dealing with more at the processing engine. So we're going to talk about the data science workbench, which is a tool that we built internally. We will talk about the Presto ecosystem a little bit, and we also have Spark ecosystem and Hive ecosystem on top, right? Presto is more for the interactive queries. Hive is more for the long-running batch and ETL type processing. Spark is for all the machine learning training and some ad hoc processing. And data science workbench is it's like a collection of tools to make it super easy for data scientists to have an IDE like atmosphere environment so that they can be productive. Right? And then we have the dispersal side of things. So we take this data and we have a subset of the data that is super well curated for our needs, like the model data, and we load that into Vertica. So a lot of the finance, marketing, sales, these teams are also interested in accessing the same data, and so they also rely on Vertica. And then the talks that you may have seen earlier, like all the visualization and dashboards and experiments, all are running on top of this, right? So at any given instant, we might be running approximately 500 plus experiments. There are, I think, literally 2,000 dashboards that people use to make decisions, right? The QPS on the machine learning models, to combine QPS on the machine learning models is north of 800,000 per second. So those are some of, again, large numbers built on top of this system. The other dispersal that's happening is the two other dispersals. One in the blue color at the bottom is dispersing the data that you may have built back into online serving systems. So consider the restaurant recommendations, right? So engineers may use a lot of Hive jobs or offline signals to compute the best recommendations personalized, and then those recommendations get loaded onto Cassandra or some such online serving system to be used by the microservices. And similarly, we have other regions where we are all active, so that's like making us resilient to region failures. So the HDFS also acts as a source of information for the other regions. Right? And then we have also invested in security and observability across the stack. Security, we have again adopted open source. We have not sort of talked too much about this in this session, but like it's Apache Knox, Apache Sentry, Kerberos-based mechanisms. And for observability, like I said, JVM Profiler is something that we build that we have open sourced, and more to come here in future. So that's like the high level view of how things are today, and we are constantly evolving. With this, I want to hand off to Reza, who is going to tell us how we are providing minutes level of freshness on petabytes of data.
Thanks, Abhi. Hi, everyone. So my name is Reza Shiftafar. I manage the Hadoop platform team at Uber. I've been with the Uber's data platform for the past like 4 years, but I only have 10 minutes to walk you guys through what challenges we overcome. So let's get started. Let's get started with the architecture we had in 2015. This is the first version of our Hadoop-based big data platform that we had. If you look to the left, you can see all different sources of our data. As Abhi mentioned, we have our sharded databases. Kafka was used a lot across the company for message passing between different services. And we have traditional single box databases as well. So we had a bunch of Spark jobs, ingestion jobs that were bringing all this data into Hadoop. The data in Hadoop was stored in Parquet file formats, mostly because of the efficiency gained when at the storage level, as well as serving it to the users who only need access to a few columns of these data. Then the modeling was happening in Hadoop on top of these data. The model tables were written back to Hadoop, and the users were able to access this data, both the raw and model tables, directly in Hadoop using different core engines that we provide, like Hive, Presto, and Spark, or notebooks. And a subset of these data, mostly the recent dates, as well as the flattened version of these model tables, were taken out to Vertica, our data warehousing solution that lets our city operators to run, to have a very fast query execution time. So this is where what we had in 2015. The data size at the time was around a few tens of petabytes, and the data latency was 24 hours. So the main problems that we were facing at the time was obviously number one, scalability. And this scalability came from two parts. One was the fact that these ingestion jobs were basically, it wasn't a real platform. It was a bunch of Spark jobs that were written to bring data from different sources. The problem with that is that it was working fine when you have tens or hundreds of these pipelines running, but then we scaled to several thousand of those, and these were source-dependent custom jobs, and it was causing a lot of operational overhead to keep them operating all the time. And this is the main motivation for the talk that Danny is going to give right after me, in terms of how we moved from a bunch of custom jobs into a real data ingestion dispersal platform. The other issue that we faced was with the HDFS itself. So HDFS works fine when you're talking about a few petabytes or a few tens of petabytes, but when you get close to 100 petabytes, all the corner cases would start showing up. And most probably it's going to be something related to name nodes, number of files, and we had to overcome those to be able to scale. And that's the main motivation for the talk that Econ is going to give right after Danny. So I'll focus on the other problems we faced. So data latency at the time was 24 hours. Again, our business is very real time, so 24 hours was extremely too slow for us. Think about the promotions we give out. We couldn't have a promotion out and wait for 24 hours to see the effect of that on our trips. So we needed more real-time solution. At the same time, we had a lot of updates on our historical data. Initially, we thought those as like corner cases. We were trying to basically find workarounds and live with those. But then we had some time and we looked at our data set and we saw that this is actually a natural part of our data sets and the way business operates. So we had to find a way to be able to deal with these updates as part of our natural workflow. And again, remember that we're talking about Parquet, columnar file formats in HDFS. So you can't go and update a single record in the past. It's not easy. And finally, the other problems we were facing was with the modeling. So let's say all your new data and updates comes in every 24 hours. The modeling was snapshot based. They have to recreate the entire model tables every 24 hours. And that was extremely inefficient. And it took another 24 hours for users to see the new model tables. So I kept mentioning that updates is natural part of our data sets. So let's dig into that and see why that's the case. So think about our most important data set, which is trips. On the left, you can see these sharded data stores that stored all these trips. It's few hundred terabytes of data. When you bring this data into Hadoop, we partition the data at day level to make it more efficient to access the data. And that is based on the timestamp when the trip actually happened. So focus on the green bars, which are the new data that are coming in. The new data, the new trips that are happening, they are mostly going to the today's partition, or if you are around midnight, it will go to the yesterday's partition. So mostly limited to very few latest partitions. And then we have 8 years, 10 years of data partition at daily level. And then we receive updates. Where does this update comes from? So think about the trips. So you take a trips, the fare is $15, that flows in as a new data, it gets stored. A few days later, you notice that, oh, you're overcharged, it was not $15, it should have been like $5. You submit a support ticket, they look into that and they say, okay, oh, it should be revised. So they change it back to $12. Now that $5 is an update happening on existing data that needs to be absorbed in the storage layer. And again, in terms of trips and fares, it's mostly limited to the past few days. But think about the way, for example, when you rate a driver. So you rated your driver next time you take a trip. So if you are not taking a trip on if you're not taking a trip on daily basis, which I hope is not the case for anyone in this room, you will rate it maybe a week after, a few weeks after. So you have an update on a trip from a few weeks ago. And this keeps going on and on. So, and again, we always have like backfillings in terms of tax and regulations. So you can have a large scale backfilling on a trips from 6 months ago. So updates is a natural part of data sets, and we had to find a solution to absorb that. In terms of the latency, the way at the time we were able to absorb all these updates was to have HBase in the middle, and all these updates were streamed into HBase. And every now and then we make a snapshot out of that, and we convert that into Parquet and put it into Hadoop and swap the two tables. The problem with that is you're having a few, the problem with that is it was taking a long time to do this. And the reason is you're having, let's say, hundreds or 200 terabytes of data where only 100 gigabytes of new data or updates is received. And because of that, because of these updates, you have to reprocess and recreate, reconvert all those several hundred terabytes of data into Parquet, which is very inefficient. At the same time, the job itself was taking around 20 hours to complete. So there was no way for us to refresh the data in Hadoop faster than once per day. And again, modeling happens on top of that. So they have to recreate their model tables too. So that was another 24 hours. So at the end, when the users were able to see the new data, depending whether they access the raw data or model tables, it was 24 hours to 48 hours to access the data. So how did we solve the problem? We introduced a library, a storage abstraction library called Hudi. Hudi stands for Hadoop Upserts and Incrementals. It basically provides you with two functionality. First, it's a storage abstraction that lets you update and delete columnar Parquet data in HDFS. So you can update trips from, let's say, 6 months ago or in the past using Hudi. At the same time, on the reader side, if you think about the readers, when a trips is updated from 6 months ago, the only way a reader can catch that update is if they do a full table scan and try to filter out based on a notion of time. That is an extremely expensive query on the reader side. So what Hudi provides is the reader can pass in a checkpoint, and Hudi gives them all the updates, inserts, and deleted records after that checkpoint, regardless of what partition that update is stored at in HDFS. So Hudi provides basically updates and delete functionality on top of existing data, as well as incremental reading on the reader sides. It's a Spark-based library, so it's horizontally scalable, and it only relies on HDFS to operate. The good news for this room is that it's open source, so you guys can go ahead and play around with this. And in fact, with all these GDPR requirements in Europe that requires historical data to be updated or deleted, more and more companies actually are using it. We initially built it only for HDFS, and they have migrated it to work in S3 as well as the S3 and Google Cloud and other different storage services too. And we have a detailed engineering blog post both on Hudi as well as our big data platform. So if you're interested, definitely check out the details. And this is how the big data platform looks like after we added Hudi, which means, again, we have all these data sources on the left and the stream of change logs that flows into, it's ingested into Hadoop. Now you don't need to have HBase or anything in between. You can directly go and apply these changes on top of the existing data into Hadoop. On the modeling side, they don't need to reprocess and recreate their model tables. They can use the Hudi incremental reader to only read out the change data, and they can use Hudi writer to only update those records. So the result of that is that the end-to-end latency was brought down to 30 minutes for the raw data and less than 1 hour for the model tables. And we have plans to bring it down even further to 5 minutes. So I only have 1 minute to wrap up. So I give a quick test of what I mean by incremental processing. So if you think about the Lambda architecture, traditionally you have a streaming side and a batch side. So what Hudi provides is something in between, so which you have the power of batch, but you can access the updated records in mini batches, which means you, again, think about the streaming side, you're processing one record at a time, which is less efficient compared to like batch processing the data. At the same time, in terms of our data set, where you have several hundreds of columns, in streaming side, you have to decode every single message, take out 1 or 2 columns or fields, and throw away the rest. When in batch mode, the data is stored on this in column 5 format, so you can only read what you need. And this is a huge efficiency gain in terms of like running the stuff. At the same time, in streaming sides, join is a really big problem. You can do some limited type of join, but in batch mode, you can do full database joins, any table across any tables. So hopefully that gives you some idea about what problem we had and how we solved that. I'll hand it over to Danny to walk us in terms of how they made all these ingestion dispersal Spark jobs into a real ingestion dispersal platform. And we're going to all be outside afterwards if you want to talk about the details, or if you are interested to learn about the openings we may have in the team.